SwayamPrabha. Digital India. Educated India.
Is simple, and we start from what you already know. Okay, what is this lecture about? Anybody read the title? Molecular orbital theory. So okay, I abbreviate it as MOT. Yeah, what all? Just whoever read whatever, just tell me about this lecture. Okay, I write it here. Quantum mechanics. So you forgot the title, or you haven't looked at it. Okay. Chemical bonding, right? Okay. Some of these elements you are already familiar with, right? Chemical bonding you are familiar with. Quantum mechanics by term you are familiar with, right? Okay, we try to combine these two aspects to understand, let's say, molecular structure. And reactivity. This we leave it for the future. If we have not enough time, we don't get in there. Okay? Okay, so we start from what you know already. Have you heard of Lewis dot structures? Okay, I have to extensively use the board. It looks like it's quite hard. Huh? Yeah? Slow. Yeah. How do I do that? Here it is start. But I again want to use this space anyway. I just wanted to test. Okay, it's easy now. Yeah. Okay. So this is something that you know, right? Lewis dot structure. What you tell me what you know about chemical bonding, whatever. Just we write it down there. We'll try to put that into quantum mechanical perspective. Okay, that's what the aim of this lecture. Okay. Yeah, just tell me what you know about chemical bonding from your +1, right? You're all +1 students, no? Yeah. Octet rule. Okay. I write it here. Okay, next. Bond store energy. Bond store energy. Yes, sir. Okay, I haven't heard this term. Are you referring to bond dissociation energy or bond energy? Yes. Okay. I see. So this is related to chemical bonding. Of course, yes. Next.
Bonding and anti-bonding molecular.
Oh, you are familiar with that. So that was in here, okay? Already. Molecular orbital theory.
So the VSCPR theory for that predicts the shapes and geometries of molecules.
Okay. So VES PER, right? What is that? VS. Is that correct? EPR. Okay. It's not EPR paradox. Electron pair repulsion. Okay. Okay. So these are all the elements that anything. One of the crucial elements you are very much familiar with, but you are missing it.
Valence Bond Theory.
Okay, that's also another theory of bonding. And you're kind of missing the basic element of chemical bonding.
So the energy is
What is the building block involved in forming a bond? That's fine. That's fine. I mean, you also have nuclei. I mean, it's not, bonding is not just due to electrons, okay? You have the nuclei, and then the attraction, repulsion between different, same set of charges and different set of charges determines the optimal bond lengths and strengths, okay? I'm missing still the fundamental construct of a bonding situation. What is that? Have you heard of orbital, atomic orbital? Right? You refer to anti-bonding bonding molecular orbitals, but we haven't gone into the chemical bonding. But to get to these molecular orbitals, you need still the fundamental construct, an atomic orbital, right? Because the bonding is formed between two different atoms or same atoms, right? So what is meant by bonding here? When chemical, by terminology you understand here, I mean you are referring to some chemical system, right? So we try to give a precise definition of bonding between two chemical species, okay, through quantum mechanics. Okay, so this means you are already familiar with. Okay. This means you are already familiar with the orbital. Our starting point is orbital, okay? Okay. So what are aspects of orbital you are familiar with? How do you define an orbital? Okay, that's what an orbital actually gives you, right? So you would, if I ask you to draw 1s orbital of a hydrogen atom, how do you do that? Kind of, since I cannot draw it in 3 dimensions. Okay. So the electron is smeared around this region. Okay, doesn't matter. If I ask you to draw p orbitals of hydrogen, they should be of the same size. Okay. Do they have some signs associated with them? Any of you remember that these two dumbbells are of same magnitude, but they have a phase, right? I call it plus minus, okay? And by the way, the shape of this orbital is, yeah, dumbbell. Okay. Similarly, d orbitals, right? I just draw one example of a d orbital. What is your favorite d orbital? Dx square, dz square, dx square minus y square. So it goes something like this. Yeah, I mean they should be ideally of equal size. Okay. How do you assign the phases? How do you assign the phases? Is that correct? Plus, minus, is that correct? Plus, minus, plus, minus. By the way, do they have some symmetry? Let's say if you start here, yeah, and you go this way, you encounter minus. You go this way, you encounter plus. Such orbitals are called. They have. I mean, it kind of reflects some symmetry, right? Have you heard of Garade, ungarade orbitals? So is this Garade or ungarade? Is this Gerade or ungerade? Okay, they could be, they are able to project it. Okay, great. Where is the pen? iPad?
There.
Okay. Oh, sorry. So, yeah, you tell me the shape of the phases of these orbitals. Just looking at one d orbital. Yeah. So, these are the correct phases, okay? They are not plus. So, they are kind of Gerade orbitals, okay? Because you start from here, you go this way, you get plus, and with the same distance in the minus end, yeah? X and minus x, for instance, y and minus y. They have so-called Gerade symmetry, okay? All the d orbitals, dx square y square and dz square, you should have dz square should be Gerade symmetry, ungerade symmetry, yeah. Okay, because you have only two lobes there, plus, minus. Okay, so we restrict our attention only to, let's say, the simplest possible atomic orbitals here, which in our case, for our discussion purposes, maximum up to p orbitals. Only at the end of the lecture we resort to d orbitals, if time permits. Okay. Okay. So the electron density is everywhere here, right? So the phase of this 1s orbital remains a constant. It doesn't have plus minus, okay, unlike in the p orbital. But you learnt that if I would like to combine these two orbitals, have you heard of the concept of hybridization? Okay. So before getting in there, okay, if that's just the byproduct of valence bond theory, okay, we'll just try to see, we assign the symmetry for these orbitals, symmetry in the sense assigning these phases, okay. Come on. Now try to see the overlap between them. When can the overlap be maximum between these two orbitals? Let's say if they are involved in bonding, yeah, when can the overlap between these orbitals maximum? Suppose I should have a p orbital, let's say oriented this way, just for the visual representation. Okay, plus minus, let's call px. So I have an s orbital, I have a p orbital, I do s plus p. Okay, what is the resultant orbital that I could get? That's what we get. Okay, if I do s minus p, what do you expect? Remember, S is spherically symmetric. S minus P. It doesn't matter whether you have minus this side or plus this side for this one. I mean, it is supposed to be spherically symmetric in the sense it can interact either with positive sign or negative sign. Okay. So this turns out to be simply suppose if I attribute this to be plus, the plus should go this side and minus, just for the consistency purposes, okay? I mean, this means that whether you make it the phase associated with this 1s orbital the same, whether it's minus or plus, it doesn't matter, okay? Just fix it to be one phase. Okay, these are the two orbitals that you can get, right? The orbitals, the hybrid orbitals look somewhat, sp orbitals look somewhat like this, right? Yeah. Similarly, you can combine different orbitals and then get to these kinds of, I still do not call these as molecular orbitals, a kind of hybrid orbitals. Okay, they still reside on one particular atom, for instance. Okay, molecular orbitals are something that you will learn that they belong to the different atoms involved in the bonding. Okay, they are not restricted to one particular atom. Okay. Okay, so we have actually learned an important concept of symmetry, assigning different phases for the atomic orbitals and trying to see the overlap between them. Okay, these two elements are going to be useful for us. We'll just exploit them in our discussion of chemical bonding. Okay. Now get back to our business. So what is chemical bonding? If I ask you to give you a 25 words or less definition, what would you give that? When I ask you what is chemical bonding, if I ask you to give 25 words or less definition, what would you say?
So it's the process by which two atoms interact to attain least potential energy state, most stable configuration.
So did you count it? It comes out to be 25 words. Okay, that's one plausible definition. Okay. So it's kind of, but any definition that we attribute to a chemical bonding is one of its characteristic. Okay, that means it's a consequence after the bond formation. Okay, what actually is chemical bonding is something that we only could appreciate after discussing these two theories in terms of probability densities for the electron between the nuclei. Okay, so lectures of this kind focus on asking these kinds of questions, which are usually complex, but any simple definition would be misleading. Okay, we don't resort to it usually. So therefore, we just try to appreciate from more qualitative perspective from these two bonding theories that we have. Okay, before getting into the theories of bonding, why do you have to learn chemical bonding after all? Where do you see its utility in all of chemistry, right? If you want to know the structure of molecules, the stable configurations, or the reactivity of these molecules, you would want to know the chemical bonding aspects, right? How the atoms are glued with each other. Okay, this glue sorts of is going to be the electronic density, which we would discuss. We would precisely define what electronic density in terms of orbitals. Okay, yeah, which is a quantum mechanical. I mean, by the way, so where do you think that these orbitals coming from? That's just a small digression. Where do you think that these orbitals coming from? Why do I say that's a quantum mechanical concept? Yeah, that's a wave function of the electron. They are simply the solutions of this equation. Okay, you are familiar with this equation, right? This is time independent Schrodinger equation, and these size what we get are 1s wave functions, whatever, 2p wave function, 2s wave function, and so on. Okay, so we define the Hamiltonian of the system and then diagonalize it in a basis, and then you get these wave functions. Okay, that's what we call electronic wave function, and this can be precisely solved for hydrogen atom. So you can have analytical expressions only for hydrogen atom, because where you have only one electron and then one proton, okay, interacting with one proton, you can analytically solve this equation and get these expressions for psi 1s and 2p. That's what you plotted here, and the plots are actually the polar diagrams. Okay, they are not in the Cartesian coordinate space, so we don't get into all those details. But the fact that you have the wave function associated with an electron, okay, indicates that it's a quantum mechanical concept. Okay, because electron is no longer a point particle here. That's what you are supposed. So that means, in other words, that takes us the Lewis dot structure that you write. Let's say for H2 molecule, you're familiar with this, right? Is absolutely an absurd concept because you are kind of localizing electron as a point particle, right? But it's kind of useful because it was the beginning of chemical bonding, okay? Lewis dot structure. And from there on, so I think he kind of introduced these structures. Lewis introduced in 1960. Quantum mechanics was developed for these microscopic systems. Of course, quantum mechanics is applicable for everything in the world, but it's most apparent for the microscopic particles, right? Microscopic systems. So the quantum mechanics came into existence in 1925 in its full-fledged form. Schrodinger equation, okay? And the philosophy of this quantum mechanics is that every particle, every microscopic system is associated with its own wave function in which all of its information is contained, okay? You just have to extract it. So once you know this psi for each of these microscopic, so you can calculate its angular momentum, energy or velocity, whatever, all the properties, okay? And then, so by then, the Lewis dot structure gave really a good insight about what a bonding is. Mainly covalent bonding, okay? Sharing of two electrons, okay? Sharing of two electrons between the two atoms. But this is not most accurate, right? What is meant by sharing of two electrons? Okay, when the electron is smeared around between the nuclei, not as a point particle, but as a fuzzy element like this, it doesn't make any sense, no? So any kind of these limited definitions would mislead us, okay? Quantum mechanics would precisely fill the gap between these point structures and then these fuzzy character of the electron inside molecules, okay? How does it explain the bonding? Okay, so in 1925 you have Schrodinger equation, you have the tool to describe all quantum mechanical phenomena associated with microscopic objects, and then I think there is a trick he played. Okay. Then in 1929, something happened. Hitler and London, okay? Not that Hitler. Borrowed the Lewis dot structure concept and then put it in a quantum mechanical setting, okay? That's what came to be known as Valence Bond Theory. The first quantum mechanical treatment of chemical bonding is given by Hitler and London, okay? Just relying on, it's just an extension of Lewis dot structures to quantum mechanical picturization of chemical bonding, okay? Okay. So that's how the VBT was born, Valence Bond Theory was born, okay? What it is, we would just see it. Okay, maybe before getting into the theory of bonding, we just discuss one, side remark about chemical bonding. So what was the status of chemical bonding 100 years ago, and what is the status now? 100 years ago, you have two atoms. This was almost 100 years ago, right? You have 2, 3 or more atoms, and then they come close by, and then because of the electrons, they stay intact. Okay. Okay, because of the mutual sharing of electrons. That's how we put it. Okay. So mostly you have, let's say, if you describe the same H2 molecule that we were talking about, you have one s orbital of one hydrogen atom, one s orbital of another hydrogen atom. So you get a situation. You get a situation. If I give this nuclei somewhere here, this you call bonding situation. Okay, we'll make it precise. What does that mean? This is usually bonding situation. Okay, you have one s orbitals of two hydrogen atoms, and they are combined to form a much bigger orbital of this kind. That's what is called bonding situation. Okay, you can have anti-bonding situation, as your friend says, where you have two nuclei sitting here. Okay, this kind of anti-bonding situation. Okay, so you see, 100 years ago, the situation was, just to explain this, you have reactants and you form products. Okay, so people were concentrating on what is the nature of the product. That's it. But 100 years later, Ahmad Zewail, okay, the Nobel laureate in femtochemistry, okay, I write it here. And Linus Pauling was extensively involved in the static aspects of chemical bonding. Static aspects by what I mean is that simply, okay, you have two atoms combining to form molecules. So you are interested in both about the reactants and the products. You are not interested in how actually it is being formed, okay, over time. So Ahmad Zewail came, and in a dramatic set of experiments using laser pulses, he kind of observed how the bond formation, the chemical bonding occurs in real time, okay, how the atoms come close by, okay, and then he took the snapshots at different times, and then how he has actually observed how the molecular orbitals evolve over time, and then finally leading to this. I mean, there are many intermediate steps, right, to get to this. From here, they have to come, these orbitals are no longer going to be spherical. As they come close by, they get deformed, and the deformation slowly evolves into this kind of ellipsoid. So these have to be timed, and that's what he did with laser pulses, okay, and he was awarded Nobel Prize for the dynamics of chemical bonding, okay, not the static aspect. Pauling was awarded Nobel Prize for the static aspects of the chemical bonding. That's what I mean, okay. So Ahmad Zewail's contribution mostly is in this region. Chemical bonding, and the chemical bonding occurs on a time scale of femtoseconds. That's why it's called femtochemistry. Okay. What is a femtosecond? Anywhere between 10 power minus 14 to 16. Okay. So it's not just a precise time scale that you have to put 10 power minus 15. It's a range. Okay. Yeah. Okay. So that's the status now. Now, this has just happened, I guess, in 2007. I guess I'm not sure about it. Maybe you can check. Okay, Ahmad Zewail's experiment, femtochemistry. And now, what is the status? So recently, there is a paper in Nature. Okay, identifying single bond between carbon atoms. Okay, Let's say, in other words, an electron is a bond with single electron. Oh, I have to. It is not an easy task to observe a single bond at carbon atoms, okay, in a molecule. So there was a recent experiment. I'll provide you the literature. If you are interested in, you can check about it, okay. It's like a single electron keeping two carbon atoms hooked. So this is called single electron bonds, okay. So that's the latest paper, just few months back. So you need advanced experimental setup to observe these single electron bonds, okay, in between carbon atoms. But yeah, yeah, just type single electron carbon bonds, okay. I'll provide you the. Okay, fine. So that is just few months back. But single electron bonds are already known, right? It's not just a new thing. What is the simplest molecule that you can have a single electron bond? That can have single electron bond. H2 plus. Yeah, you have just one electron with two hydrogen atoms, right? This is all, but it's unusual to have a single bond between, single electron bond between carbon atoms. That has been observed. So this means that there is plenty of room in the current scenario about the investigation of chemical bonding using laser pulses and advanced experimental techniques. Okay. So you kind of have all those bonds from your inorganic chemistry, banana bonds, 2 electron, 3 center bonds and all. These have evolved over time, okay, from what was Lewis simple dot structures between two simple atoms to much more complex chemical bonding, okay. Yeah.
If we have such complex bonds like single electron bonds, banana bonds,
Yeah.
what are the limits of the bonds?
Limits.
Like what can a bond not be?
Yeah. What can a bond not be?
Yes.
Yeah, that's what. So maybe you can ask me this question after we discussed MOT and VBT in terms of electron densities. Yeah. Okay. We'll discuss that question in the context of MOT and VBT theories. Okay, what are other elements that we need as a preamble to kickstart our quantum mechanics of chemical bonding? I see you're familiar with orbital, symmetry and overlap of orbitals, and then you kind of appreciated the current status of chemical bonding, okay? And then you kind of appreciated the historical context of chemical bonding, how in relation to quantum mechanics, okay? So then let's get into the theories of bonding, okay? But before getting in there, I just want to show you one picture, maybe here. I guess I drew one picture, what we talked about. Can I operate this? It's not going back and forth. Yeah, you can go to first page, first few pages. How can I go? Oh, it's only single. I see. Okay. Uh-huh. No, the whole document. I see. Meanwhile, we'll just proceed further. Okay, valence bond theory and MOT. Okay. Instead of and, I write versus. Okay. Much of the histories of these two theories goes back to the contention between its respective proponents, okay? Because the overzealous supporters of one theory says that the other theory is wrong. So, and vice versa, okay? But any theory can be used unwisely, right? I mean, it's up to us how wisely we would like to use any theory, yeah? So therefore, I mean, it's always, but both these theories offer crucial insights of chemical bonding in terms of quantum mechanics. But there are situations where one theory fails and the other theory is successful. And similarly, we'll see one example of that kind where VBT fails and MOT is successful and the vice versa. Okay? But it's always better to learn both the theories, because as a chemist, if you limit learning these two theories to one, let's say if you just learn one of them, it's like you are a carpenter who has let's say hammer but doesn't want to have a saw. So you are just kind of limiting your skills by limiting your tools, right?
So,
Yeah.
is that like a dual nature, sir? Like how that dual nature of light, that's a dual nature for
Dual nature.
bonding?
No, it's not the dual nature. These are theories of chemical bonding. It's like how a bond is formed. They have different ways of explaining the same thing.
So in the same way that light can be we explain light as molecule and light as a wave, we can also explain chemical bonding in terms of PVT and MOT.
Yes, these are two theories. Yeah, absolutely, yes. Yeah. Yeah.
How would we primarily differentiate between EBD and MOD?
Once we discuss them, you will appreciate it, right? Okay, fine. So, do you understand? So, our goal is to be familiar with both these theories so that we enhance our toolbox, okay, to be more skillful in understanding chemical bonding, okay? Yeah. Okay. Valence bond theory. What is meant by valence in it? Yeah. So we are concerned about only the outer valence electrons, which are mainly responsible for the bond formation. Okay. Okay. So let's start with the simplest example. The H2 being the simplest example, right? We'll try to appreciate the H2 molecule. Okay. So suppose our assumption is that, suppose if these two hydrogen atoms involving in the bond formation are far apart from each other, that's what happens initially, right? At time equal to t equal to 0, they are very far from each other. And then they have their respective electrons sitting in 1s orbital, right? That's what we have drawn there, okay? So when they are far away from each other, the total wave function of the system containing two particles, let's imagine that these are two particles far away from each other, turns out to be the product of individual wave functions. Okay, so I have a total wave function for a two particle system, and these two particles are far away from each other. Okay, and these have their own wave functions. The total wave function, what I am trying to say is that, so I call hydrogen, two hydrogens being A and B. I label them as A and B, okay? So I have the wave function for A, wave function for B. And this is my total wave function when the two hydrogens are very far away from each other. Okay, that's the first, crudest and simplest approximation that I can make. It's like you have two non-interacting particles, non-interacting system, right? So, I mean, how many of you are familiar with particle in 1D box? Particle in 1D box? Okay, it's fine. Okay, in quantum mechanics, if you have two non-interacting systems, the energies turns out to be the sum of these two systems. The wave function turns out to be the product of these two systems. Okay, that's what we use the fact.
SwayamPrabha. Digital India. Educated India.